Okay, so we've written down the content of renormalization conditions 1 and 2. And maybe one thing that I'd just like to stress is that you can see on the right-hand side of this equation, we've got I over p squared minus m squared plus I eta. That's completely finite. In particular, there's no dependence on epsilon, m, or g. Whereas on the left-hand side, we've got dependencies on the parameter m that appears in the Lagrangian. Well, that's certainly divergent. And then we've also got the loop integral there, which is divergent. Okay. Now, we've got three renormalization conditions. So let's now try to summarize in a similar way. Oh, let me change color. Let's try to simulate. Let's try to summarize in a similar way the content of the third condition. So content of 3. So what is 3 telling us? Well, 3 tells us to add the following 3 diagrams. Remember that we've dropped the external legs. So that's why I'm drawing the external legs as little stumps. But we had some one loop diagrams. This was the condition for the coupling. There's the little stumps. Plus, we had another one loop diagram that takes this form. There's the stumps. And then finally, okay, so remember you must drop the legs, but I'm just going to show where the legs go, okay? So there was a leg that came up here. The external legs, of course, are dropped. And then there was a leg that came around here like this, okay? But the external legs should be dropped. And this was equal to G physical times 4 factorial I. Once again, on this side of the equation, you have divergences. So it's divergent. And things depend on epsilon, m, and g. But on this side of the equation, things are again finite. Good. So that's the content of our third renormalization condition. What the claim is, if you have a theory that is renormalizable, the claim is that any correlation function you choose to calculate to any loop order will be finite using only these 3 conditions, okay? So I want to give you an example of how this works. I'm going to look at the 4-point function, and I hope that after we've done this exercise to the 4-point function, I hope that after we've done this exercise, you would be able to check for yourself that other correlation functions are finite. But it's always the same sort of a calculation. So let's look at the 4-point function. We're going to look only at the connected piece, okay? And of course, we're working to one loop. So don't forget that. That's in fact the thing that's going to be tricky, as you will see. So if we write down a sum of all of the one loop diagrams, well, certainly we've got that. Then we will have this. We will have this. We will have that. We will have this. So each of the external legs has been dressed by a loop. And then we've also got the loops of this form. Okay. Good. And there's one more diagram. And this is the one where the legs really do a bit of twisting. That goes up to there. And this one comes back here. Okay. So I can do better than that. Let's try to. That doesn't look very clear. So let me try to draw this a little bit better. I don't know if this is going to be better or not, but let's just try. So this leg, okay, comes down here and out there, and this leg comes through there. Okay. Okay, so there are the diagrams. I think you've got the idea. what's important is I've drawn the complete set of diagrams at one loop, and I've only drawn the diagrams that are connected. And the question is this sum finite? And is it finite by only using the conditions 1, 2, and 3? So let me tell you what the basic idea is. So here's the basic idea. Remember, this double line over here, we said was finite, okay? And we said it was the sum of the original propagator plus the one loop correction. So I want you to look at this particular quantity, okay? And this will illustrate nicely the idea. So we've got that. So what is this equal to? Well, let's look first at this leg, which is in the upper left-hand side. So I can replace that leg by two terms. Okay. There's the first term, and then here is the second term. So I hope it's clear what I'm doing. This fat line is just the thin line plus the one loop correction. So I've replaced the fat line by the thin line plus the one loop correction. Good. Now, let's do that for the second line that's in the upper half. Okay. So for the first diagram, we have that plus we have that. So the first diagram that I had on the first line becomes these two diagrams sitting over here, okay? And now let's rewrite the second leg. So we'll have this. And we will have this. Now, we said that we are working to one loop, okay? This diagram becomes the sum of those two. Now, if we're working to one loop, notice this diagram over here is a two-loop diagram. So that we should not include. That would be h bar squared. That's a higher order of h bar. We can't include this without properly including other effects. So this two-loop effect should be dropped. So we'll drop it, okay? So that diagram we must cancel out. Good. So in fact, so this is the subtle point. This is the thing that you've got to watch. When we are translating the thick lines into the thin lines, there's a piece that doesn't get translated because it's order h bar squared. It's two loop, okay? So now let's keep going. So for the first diagram that you see above, well, I'm going to now start to rewrite the leg at the bottom and on the left. So I can have that first, or I can have this. Okay, so that's from the first diagram that you see on the line above. From the second diagram that you have on the line above, well, certainly you'd have this. And then the other correction that you could write down, well, let's just write it down and make sure that we're happy. This diagram, you again would not sum. Why wouldn't you sum it? Because that's again order h bar squared. So we've been neglecting that term. So now let's go to the third term. And for the third term, again, there's two contributions. So we would have this with the loop there. And then if we were really just rewriting that fat leg, we might also think that we have this. And I think that you know again that we drop that term because it's got order h bar squared. Okay. So now rewriting the last leg, well, what would we have? From the very first diagram, we have this. And then we could also have this with the loop dressing that fat line. For the next diagram, you see, I've got the fat line, but I've already got one loop. So I can't introduce another loop. So that's all I get from that second diagram. From the third diagram, all that I'm going to get is that, okay? And from the fourth diagram, all that I'm going to get is that, okay? And that's it. So now we have this nice equation. Let me just put this down over here. This is with the fat legs. This is actually the sum of the fat legs, which is great. So this is what we've gotten. And the only subtle point in this computation is that we had to neglect certain terms of order h bar squared. And that's always the subtle part of any of these computations. So let's go ahead and let's now look at the Green's function that we were analyzing. Okay, let me copy this to downstairs, and then we will rewrite it. Good. So let's duplicate that. Now let's take it downstairs. Now take a look. Here's G4 connected. But I think that what you can see immediately is the first 1, 2, 3, 4, 5 diagrams are replaced by that single diagram with the fat lines. So this will simply be equal to, let's write it nicely, is just that. And then plus we would have this, plus we would have that. And then for the last diagram, okay, guys, I'm going to do my very best here. Let's see if I can draw this slightly better than I've managed to so far. This leg would go out there, and this leg would go down there. Okay. So this is we've reduced things now to a sum of 4 diagrams. Now, if we wanted to change these legs on the outside, so here's my claim. My claim is that, for example, for the second diagram, I can write this as a thick line sitting over there. And then this leg going over there, that leg going over there, and 2 thick lines sitting over here. Why is that? Well, what's the difference between a thick line and a thin line? The difference between a thick line and a thin line is a loop. So the thick line minus the thin line is a loop, but over here, we've already got a loop. Okay, so in exactly the same way that we were neglecting all of these additional higher loop effects, the approximation that I make in going from this thin line to the thick line is a higher loop effect. So to one loop order, it's perfectly valid to rewrite the second diagram into that third diagram. So this replacement over here is perfectly accurate at one loop order. And we can make the same statement for this diagram. Again, what we do is perfectly accurate at one loop order. And for this diagram, it's exactly the same. One loop order, what we've done is perfectly accurate. Here we are. And then let's pull this one down the bottom through here, through there, up there. Okay. So we could make all of the external lines thick because to one loop order, that's perfectly okay. Now look at what we've got. If we had to pull those thick lines off, then what's the sum of stuff that we've got? Well, the sum of stuff that we've got is exactly the stuff that gets added in diagram 3. So actually, I should have introduced some notation for this. So let's do it now. Let's call this, there's the vertex. Let's put a circle around it, okay, to indicate that it's been renormalized. So when we sum these 4 diagrams over here, they give us that over there. And so when we sum these diagrams sitting over here, this is nothing but that So what do the sum of these four diagrams do? Well, summing the loop, okay? Summing the loop turned a thin line into a thick line, and summing these four diagrams turns a thin vertex into a fat vertex. Okay, so that's the content of equation 3. Summing these four diagrams changes the original thin vertex into this fat vertex. And summing these four diagrams over here turns our thin vertex into that fat vertex. So that's what we finally get. And what is this expression? Well, this expression is minus 4 factorial IG physical. That's the value for the vertex. And then we've got I over P1 squared minus the physical mass squared plus I eta. We've got I over P2 squared minus the physical mass squared plus I eta. We've got I over P3 squared minus the physical mass squared plus I eta. And then we've got I over P4 squared minus the physical mass squared plus I eta. And notice in this final expression, it does not depend on epsilon. So we can set epsilon equal to 0. We come back to 4 dimensions, no problem. It doesn't depend on m and g. So this is perfectly finite. There's no divergences here. It only depends on quantities that we've actually defined and measured. So that's wonderful. This is the demonstration that the 4-point correlation function actually is finite. Great. We'll continue in a moment.